the sharing on the screen. Okay. So here I can see the presentation.
Yeah,
already.
now it's better. Yes, now it's better, Sergio. Perfect.
Yeah.
So the name of the work is an energy-based time adaptive spectral filtering technique for DGSM. Okay. So the contents of the presentation are the next. First, I'm going to introduce the motivations. Then I'm going to explain Burgers and energy equations. Then I'm going to introduce the proposed filtering framework. I'm going to present some results and finally some discussion and conclusions. So the motivation is the next. In the context of CFD, computational fluid dynamics, nonlinear partial differential equations are used to address turbulence phenomena. Also, physically, one should represent, for example, propagation fronts, shear layers, etc., which cannot be fully represented numerically due to discretization. Then these subgrid effects should be well managed in order to accurately capture dissipation range of energy. This range right here. And we're representing these continuous functions with continuous ones, as in spectral element methods. Gibbs phenomenon arises. So the formula for disaster when solving this kind of problems with spectral element methods is discontinuities plus nonlinear terms equals aliasing spelling, which produces numerical solution divergence. All these issues comes with high order methods. So the solution is to use stabilization techniques as filtering, hyperviscosity, aliasing, slope limiters, and others. But there is an additional problem, which is that none of them have an unambiguous way to be defined, since every technique has some movable parameters. The idea here is to relate these parameters with physics by analyzing the behavior of a quantity that must be conserved as energy. Okay. Particularly in filtering, there are a lot of disponible functions and some parameters to choose. And the general rule to choose them is filter as much as needed, but as little as possible. And then there is no a certain way to it. And why filter? Because it's still widely used, and because it is simple to apply, since it becomes just a matrix vector multiplication per element after every time step. So the objective will be get a rule for applying it to a numerical solution using filtering through an energy analysis over Burgers equation. So the Burgers equation, which is the canonical to analyze motivation kind of numerical issues. It is a means to test the proposed technique. It is nonlinear, it generates propagation fronts, and is a previous steps towards Navier-Stokes, usually. Here T is time, X the spatial dimension, U is the dependent variable, velocity in context of CFD, and nu, the viscosity coefficient. If nu equals 0, the implicit version is obtained. In addition to well-defined initial and boundary conditions. Here omega is a closed compact domain. Okay. So this is the analytical solution to the one-dimensional version of Burgers equation, which is found through the Hofstadter transformation. Here U sub 0 is the initial condition, and all these functions are Gaussians. The solution U is well defined for every t and viscosity is greater than 0. But when computing the integrals involved, these integrals, they must be solved numerically. I'm using a Gauss quadrature with about 248 nodes. 2048 nodes. But some underflow problems arises when multiplying these functions. So computationally, it can be solved only for viscosities greater than 2.5 times 10 to minus 4, approximately. Okay, this is an example of the analytical solution for the initial condition minus sine of pi times x, which will be my framework. I'm going to reproduce the graph. Okay. It can be seen the steepening in the middle of the domain. due to nonlinear transform and the diffusion, which is the damping of the solution. Here the value of the viscosity is 0.01. Okay. Now, for the implicit case, the analytical solution could be found with characteristic method. Here the plot shows the characteristic isovelocity lines over time. The genuine solution becomes multivalued from critical time on. The critical time is this dashed line, from which a physical relevant solution must be settled. With this initial condition, the same as previous, critical time is 1/pi, right here. An important remark is that after critical time, in this case, there is a natural damping on the energy due to characteristics collide. Okay, now talking about the numerical solution. For the numerical solution of Burger's equation, this is the model decomposition of the solution, which is done through a family of orthogonal polynomials, Fourier, Chebyshev, Legendre, etc. N is the maximum order of the chosen family, phi. U hat are the modal values or frequencies. K the number of elements. And an additional remark about discontinuous Galerkin methods is that the boundary conditions are imposed via weak form, and a numerical flux appears, which could be monotone, lax flares, and others. And about the filtering, this is the way to do it by introducing a filter function sigma into the model decomposition, which is a low pass filter that must satisfy these conditions right here. S is said to be the order of the filter, and this notation here means the L derivatives of the function. Okay. The most common filter function is the exponential one, in which coefficients alpha and order S must be chosen. The lower the order S, the stronger the filter. Additionally, a cutoff value n sub c might be settled. That is to say, the filter will act for i's greater than n sub c, but the order, unusually the order S of cutoff n sub c are settled based on modeler experience. So we will present a strategy based on energy conservation to compute them. To do that, we need to compute the derived energy equation, which is obtained by multiplying Burger's equation by U. This function can be integrated over any domain omega in order to get energy global behavior. Okay. Reducing and integrating by parts, this equation is obtained, in which every term is related to a portion of the global energy. So every term is right here is the actual energy of the solution, E, the energy flow due to nonlinear term, E sub NLF, energy flow due to viscous dissipation, S sub BF, and the energy dissipated due to viscosity, E sub BD. Okay. Now our this every term can be computed over time with a time integration method. The actual energy term is right here, so we can use the Parseval's identity for orthogonal polynomials to compute numerically through the modal values of the solution. This is the term of accumulated nonlinear flux of energy. Then we have the term of accumulated dissipation flux of energy, is right here. And finally, the term of accumulated pure viscous dissipation of energy is right here. Again, for this case, we can use numerically the Parseval's identity to compute this integral. But in this case, this means the modal values but of the derivative of the solution. Okay, now a balance of energy can be selected. Here E sub 0 means the initial condition, sorry, the initial energy of the system, and the balance is then the next. E sub 0, the initial energy of the system, must be equal to the actual energy of the solution in some time t, plus the accumulated energy that has flux due to nonlinear term up to a time t, plus the accumulated energy that has flux due to viscosity up to a time t, plus the accumulated energy that has been dissipated up to some time t. And this graph represents every term conceptually for a domain omega. Okay. Okay, now from the combination of solving analytically or numerically the Burger's equation by one side and the integrals involved in energy equation on the other side, this table pops up. So we are going to analyze the 4 spots here. The numbers here are inverse, sorry. Spot 1 implies solving everything analytically. In this case, one gets a perfect match in the balance for any viscous case and for times between 0 and critical time from the visit 1. And when I say perfect match, that implies that the equality of the balance equation, this equation, holds perfectly. Spot 2 means solving integrals analytically over the numerical solution of Burger's equation. And this implicitly means to find the error equation for the numerical solution, which is a hard task to do even for simple equations. So since spot 1 and 2 are quite impossible, we are left with spot 3 and 4. And since we have an analytical solution to Burger's equation, we can compute integrals numerically using a Gauss-Loato quadrature, that is to say Parseval's identities and model decomposition. And the analysis on this spot, numerical integration over analytical solution of Burger's equation, will give us what we call the energy rule to apply to a spot, to this last spot, which is everything numerically, which is the one-hand case, and the ideal case. That is to say, solving everything numerically. Okay. This plot lives in the spot of numerical integration over the analytical solution and shows the evolution of the energy balance over time, computed with numerical integration or analytical solution, and for different Reynolds numbers. For the integration, n equals 19 and k equals 9. In this case, the initial energy of the system is 1. Note how before the invisit critical time, which is plotted here, this dot line, there is a perfect match in the balance. That is to say, it is equal to 1, but due to numerical errors after critical time, the perfect match is lost, and the balance take a trend upward or downward. Dashed lines means that for those cases when computed numerically, the solution to Burger's equation diverges up to infinity. So these plots right here are an extension of the previous analysis to other combinations of number of elements and polynomial order. The different kind of rates represent the trend of the energy balance over time, upward, downward, or perfect match. Remember, this is numerical integration of an analytical solution of Burger's equation. Know the correlation with Reynolds numbers of the structure of the plot. The lower the viscosity, the higher the viscosity and the lower the Reynolds number, the closest to all perfect match, which is this case right here, for Reynolds 40. And when Reynolds tends to infinity, the closest to always downward trend, as it is the theoretical case when viscosity equals 0. So the hypothetical case of Reynolds equals infinity, because viscosity is equal 0, downward is always, the trend is always downward. In the middle, there is a zone of where the trend is upward, but it moves towards the upper right corner as Reynolds goes to infinity. Now, in this plot, are included the regions in which the numerical solution of Burger's equation are stable or unstable, without using stabilization techniques, of course, depending on the combination of numbers of elements, polynomial order, and Reynolds numbers. As it is natural, as Reynolds numbers tends to infinity, the instability regions grows. Being always unstable for the implicit case. Okay, so the result of this analysis is what we call the energy rule, which is that for unstable regions, the energy balance trend must be downward. And the goal is to force this rule over the solution through filtering and adaptively over time. Okay, to do that, this pseudocode shows how to do it. Blue steps are additional steps to a classical solver. So if we set the numerical and physical parameters, then we set an initial condition U sub 0. We then compute the initial energy per mode. We set a filter function initially as all ones, which when applying to the solution, when applying it to the solution, it doesn't change nothing because it's just once. We enter into a time loop. We advance the solution. Then we compute the energy terms of the balanced energy equation per mode. We check the trend of the balance, and if the trend is greater than 0, we recover the difference from the last mode on. That is to say, starting from higher frequency modes, recovering the difference enough to make the trend equal 0 at least. And this will give us what I call NA affected modes, and this must be done by element. Now the filter function can be updated using the exponential one. We have used the exponential one with these parameters. So the cutoff n sub c will be equal to n plus 1 minus the number of affected modes. Alpha will be equal to minus logarithm of epsilon, where epsilon is machine precision. And S will be equal to closest even to the number of affected modes. Then we end the if. Then we apply the filter function, and finally the time loop ends. So as you can see, the filter function is adaptively updating over time, depending on whether there is a trend upward or downward of the balance of the energy. Okay, so this slide shows the number of basic operations of the additional blue steps, being a total of the order, the total of the order of number of elements times polynomial order per time step, which is not greater than solving the Burger's equation itself, whether by explicit method or by implicit method. And the computational cost is linear, depending on the number of elements and the number of nodes per element. So the results will be presented by a comparison with classical methodologies, specifically spectral vanishing viscosity, SVV, and filtering, classical filtering techniques. The particular case to evaluate the performance will be a polynomial order equals 20 and number of elements 10 with legendary polynomials. It will be tested with implicit case, being in this case the critical one, without loss of generality, extensible for unstable viscous cases, according to the previous energy analysis. I will present enormous variable versus time and error structure on space for the final time step. Here, plots A and B shows the infinite norm error over time. The first one shows is in logarithm scale, and the second one is in natural scale. Black contiguous line is the performance of the proposed methodology. Dashed dot line is a spectral vanishing viscosity of order 1. That is to say, second order of diffusion hyperviscosity term. And dashed lines are classical filtering with different orders. Okay, in both cases, the proposed methodology can be seen as a lower envelope on the error of classical filtering techniques. And at the end of the simulation, the best infinite norm error is achieved by the proposed methodology. And remember that infinite norm is related with point-wise convergence. Plot C is the mean error or is the mean order of error over time. And it can be seen that the proposed methodology performs as well as the classical filtering techniques on preserving mean convergence. Now, the most remarkable result here is that when the solution does not need a stabilization at all, the proposed methodology keeps it intact. So see how the error is well preserved in the beginning of the simulation, 4 times between 0 and 0.2 approximately. Okay, now this plot shows the error structure for in the MVC case for the final time step of the proposed methodology. Contiguous line, which is the contiguous line, spectral vanishing viscosity of order 1, which is the dashed dot line, this right here, and best classical filtering technique of order 16, which is the gray dashed line. The proposed methodology preserves convergence away from the discontinuity, which is right here in the middle of the domain, as well as best classical filter result. And also it had the best performance on preserving the error near the boundaries, being SBB the worst. But 3 approaches have a similar behavior near the discontinuity, which is the harder problem to address. But some literature achieves this goal and can be merged eventually with this new framework. So, as some remarks for discussion, proposed methodology can be seen as a slope limiter of the evolution of the balance of energy over time, since we are forcing that balance to be downward for unstable cases. It is a framework rather than a new standalone filtering technique, because in this case we are using exponential filter. But we argue that any other kernel function might be used as soon as a relation between the number of affected modes, what we call affected modes, and the adjustment parameters is settled. The convergence is ensured whether the numerical solution naturally blows up, but nothing can be said about the spurious oscillations that appears, but really does not affect the energy balance evolution computed numerically. The trends plot, which is the plots of rate of energy computed numerically over the analytical solution of one-dimensional Burger's equation, was made with brute force in this case. But there is a question here that it is maybe possible to build just with functional and spectral element analysis. And about the extensibility of the methodology, the analysis used to get the numerical energy rule might be extended to another dimensions or equations whenever an analytical solution and test framework is available. And finally, as conclusions, a new framework was developed based on purely computational analysis of the derived energy equation of Burger's equation. It was tested against classical filtering approach and classical first order spectral vanishing viscosity. It acts as a lower envelope about the error of classical filtering techniques. It was proven that the new methodology framework preserves the mean convergence away from the discontinuities and perform as well as classical stabilization approaches on point-wise convergence as a secondary effect. I will mention this later. The new methodology avoids ground selection of filtering parameters since these are automatically computed. And finally, and the most important, is that the numerical solution of Burger's equations remains intact for those times when it is no need of stabilization at all. And some discussion about the feedback comments of my reviewers, the most important comments, the most relevant comments of my reviewers. And there was a comment about pointwise convergence, the Van de Ven theorem. It is mentioned that the convergence as exponent S of the filter, the convergence is ensured as exponent S of the filter is proportional to the number of modes. In this case, is proportional to the number of affected modes. Then it is not a direct consequence of the methodology, but it is by the way the filter function is defined. Because at the end, we are actually using exponential filter function. Was a comment about the parallelisms with entropy stable techniques. In this paper, the main one, symmetric discontinuous Galerkin spectral element discretization, and its relation to this scheme for finite differences methods by Gassner. What they say in this paper is that DGSM with Gauss-Lobato distribution of nodes is equals to finite differences with this scheme using a diagonal norm operator. And what they do is they split the nonlinear term in a conservative scheme with skew symmetric technique. They do it for the implicit Burger's equation, but they need to use conservative flux, specifically Lax-Friedrichs kind of flux. That was a question that we had with Professor Jorge at the beginning of the research related to the kind of numerical flux that we are using. But since we are using the nonlinear term as it is, we never try skew symmetric versions. It would be nice to, in the future, to apply the energy analysis on this methodology to know how it, what is the performance. There was another comment about energy preserving techniques. This is the main paper by Kennedy Gruber and Gruber. It's actually the same methodology as the previous one, or very similar, because they propose convective forms of the nonlinear term, which minimize energy aliasing, and they propose new quadratic and cubic skew symmetric forms. And they say that by doing that, they reduce filtering needing when solving Navier-Stokes equation. But they didn't say that they reduce completely filtering needing. So again, it would be nice in the future to combine this, the proposed methodology with this one to see how it performs. And finally, a comment about entropy viscosity techniques. This is the main paper by Kermon and Paschetti and Popov. This Professor Paschetti is the leading researcher in spectral vanishing viscosity methods. And what they do is they use a similar approach based on energy to adaptively compute the viscosity coefficients in a space, and to apply then spectral vanishing viscosity. But the analysis is pretty similar because they are basing this in an energy analysis, but they use spectral vanishing viscosity approximation, and I'm using instead filtering technique. Okay, that were the main comments of the feedback, and principal references on principal topics that I have touched. This right here, and that's all the presentation.
Okay, Sergio, thank you very much, especially for accomplishing perfectly the time. just expend your 30 minutes precisely. So thank you very much for that, which is quite difficult sometimes.